Welcome to this next class. In previous classes, what we have looked at are catalytic reactions. We have seen the mechanism of these catalytic reactions. Reactant gets adsorbed, reacts on the surface, and product desorbs. And we could derive rate expressions for this whole mechanism, considering one of them to be rate controlling stem, whether adsorption is rate controlling, reaction is rate controlling, desorption is rate controlling, and correspondingly we saw how the initial rate versus concentration or partial pressure of the reactant changes, and based on this we could decipher a mechanism. And we also talked about how we decipher mechanism based on experimental observations, what kind of experiments we need to carry out so that we can decipher what is the mechanism of the reaction, and how do we quantify the rates, and how do we calculate all the parameters that are there in the rate equation, and how to use them for design of a reactor. Let's go forward in our course. What we are going to look at now is the next part of the course, and as I said, the next part of the course is related to the fifth part of this course is related to still solid catalyzed reaction, but now we are looking at diffusion and reaction inside the porous catalyst. How do we define what are the possible internal and external heat and mass transfer resistances in catalyst pellets, and how do we use all of this information for design of such reactors. Just to get you started and revise what we have done so far in last few lectures, I would like you to write steps involved in solid catalyzed reactions. What methodology should be followed to find rate expressions for catalytic reactions? I want you to draw concentration profiles when reaction is limited by external mass transfer or diffusion or intrinsic kinetics. Remember, we are drawing concentration on the y-axis. We are drawing concentration on the y-axis. Let's say a reactant is A, concentration of A on the y-axis versus distance. This is our gas bulk or fluid bulk. All this mass transfer is situated, we are assuming film theory. So this mass transfer resistance, all that mass transfer resistance is concentrated in this liquid film or a fluid film. If it's a gas reaction, it's a gas film. And then there is porous catalyst here. I want you to draw concentration profiles. This we have done in our previous lecture. Just to refresh your memory, I want you to do it again, because these are the considerations that we are going to take in this lecture. What happens when external mass transfer is important? What happens when the diffusion and reaction inside the catalyst is important? Or when I say important, what we mean is rate determining. It is a slow step. Mass transfer is a slow step, or the diffusion and reaction inside is the slow step. Okay. Here is some more little bit about revision that I want you to do. We have defined, or we have classified catalyst based on the pore size that is there. We had defined it based on macroporous, mesoporous, or microporous. Recall the definitions. Recall what kind of pore sizes is there in these conditions, in these catalysts. Bulk diffusivity in the gas phase is about 10 raised to minus 5 meters square per second. Bulk diffusivity in the liquid phase is 10 raised to minus 9 meters square per second. It's just an approximate order of magnitude value. It is not that every value will, for every gas it will be 10 raised to minus 5, or for every liquid it will be 10 raised to minus 9. It depends on the temperature, it depends on the nature of the liquid, viscosity of the liquid, and so on and so forth. When the solute or when the reactant is diffusing through these catalysts, through these pores, then if we have liquid phase diffusion, we typically account for that in terms of the restrictive factor. Okay. And if it's a gaseous component, we define typically in terms of Knudsen diffusion. Right, Knudsen diffusion. And recall how we had calculated this in our previous lecture. So what I want you to do now is think about a catalyst. Let's say this is our catalyst. Right now you can think of it as a cylindrical catalyst or spherical catalyst, or for simplification you can think of it as a catalyst slab. So Cartesian coordinate systems we can use. Let's say pseudo first order rate constant based on the catalyst volume. Catalyst volume is K 1 per second. I want you to write an equation that describes diffusion and reaction inside the catalyst slab. So what I'm trying so remember, we are talking about a slab. Now the catalyst is not like this, we are talking about a slab. So our slab catalyst is like this. We can define half the slab, and this is the catalyst slab. And our reactant is here. So fluid is here. Gas or liquid or fluid is also here on either side. Remember, in a packed bed, fluid is going all around the particle. That's why we are considering fluid on both sides, and we are considering because then it becomes a symmetric case. Okay, there is an external mass transfer film here. There is a bulk here. Okay, because of symmetry, we can only look at the one half of this catalyst. We don't have to look at both the halves. Okay, I want you to write down an equation that describes diffusion and reaction inside this catalyst. Inside this catalyst. How do we solve this equation and how do we calculate rate of reaction? These are the considerations that we are going to make. If there was no pore diffusion limitation, what would rate have been? So when pore diffusion is limiting, or when pore diffusion is reducing or restricting the rate, how do we calculate the rate? And if pore diffusion was absent, pore diffusion limitation was absent, that means pore diffusion was occurring at a very high rate, what would the rate have been? And if that is the case, then we can define something like an effectiveness factor of the catalyst particle. These are the considerations that we are going to make, just like we have defined effectiveness or fin efficiency in heat transfer. Recall from your undergraduate lectures. So try doing this for yourself, pause and then go forward. Okay, here is that slab again. Think of this, we can think of this. So our slab is here. Let me write. So our film would be here. So film would be here and bulk would be here outside the film, right? So we are not worried about the resistance in the film. We are saying mass transfer to the surface of the catalyst is very high. Okay. And we are going to write for diffusion and reaction inside this catalyst slab. We are going to take a small differential element x and x plus delta x. So this is a differential element where diffusion and reaction is occurring. If we use our differential equation that we had derived in our RTD equations, RTD lectures, we could write this expression. Right? We could have we can write this easily. It takes into account convection, diffusion, reaction. All of that we have already seen. We have already derived this expression. Right? So now what is inside the catalyst slab? Inside the catalyst slab, convection is 0 and we are looking at steady state. So del Ca by del T is 0. Convection is 0. That means this is 0. So our equation simplifies to effective diffusivity d square Ca by dx square plus Ra is equal to 0. And remember, we are writing for, let's say, a first order reaction. So Ra is minus Kca. So effective diffusivity in d square Ca by dx square becomes Kca. Alternatively, if you want to think, this is the area through which diffusion is occurring. So we can write flux on this face. Flux would be minus d effective dCa by dx at x. Flux at this face would be minus effective diffusivity dCa by dx at x plus delta x. So we are writing in what comes in minus what goes out. In minus what goes out. In minus out must be amount that is reacted in this. So amount that is reacted is nothing but Kca, that is the volumetric rate. And if I multiply by delta x, we'll get the in terms of flux. Just to make you comfortable, d effective has units of meter square per second. dCa by dx kilomoles per meter cube per meter, right? And then K 1 per second, Ca kilomoles per meter cube, and delta x meters, right? So this will be flux units, kilomoles per meter square per second. All right. Okay. So we get the same expression whether we derive from first principles or we derive for this control volume. They are essentially the same, right? They are no different. Both are based on control volume. What are the boundary conditions? At x equal to 0, what can we say? At x equal to 0, concentration of A let's call it as concentration of A at the surface, CAS. At x equal to L, we have symmetry condition. So symmetry condition, how do we describe mathematically? Del CA by del x equal to 0, gradient 0. Okay. I want you to think about what would be the equations for cylindrical and spherical catalyst particle. Try starting from here itself. From here itself, I want you to write for cylindrical slab or cylindrical catalyst and spherical catalyst pellet. You should be able to do this now. Okay. We'll solve for Cartesian, we'll solve for a slab further. So we want to solve this equation with respect to these two boundary conditions and get a concentration profile Ca as a function of x. Okay, do that for yourself. Pause the video, do it for yourself. Okay, one way to do it is, before we solve, let's make it dimensionless. Okay, reason for making it dimensionless is then it becomes independent of the actual concentrations. Okay, so how does Ca, we want to make Ca dimensionless, we want to make Ca go from 0 to 1. Only way we can do that is if we divide by surface concentration, and x we want to make it dimensionless by defining x bar, so x will go from 0 to 1. Okay, so now our equation becomes effective diffusivity CAS d square Ca bar divided by L square dx bar square, and K CAS Ca bar. Okay, you see, now small correction, this should be Ca bar. Okay, and this CAS will now cancel. Okay. So this gives us our differential equation in the dimensionless form. So because it is in the dimensionless form, it is applicable for all conditions, whatever be the K, whatever be the L, whatever be the effective diffusivity. So this is our dimensionless equation. What is the dimensionless parameter? Dimensionless parameter is our d square, is our this parameter KL square by effective diffusivity. We are going to call this as phi square, and this phi will be square root of KL square by effective diffusivity. We are going to call this as Thiele modulus. What are the boundary conditions? Boundary conditions are x bar equal to 0, that means at the surface, left surface, x bar equal to 0, Ca bar is equal to 1, right, from here, and x bar equal to 1, center line, gradient is 0. So in terms of gradient, it will be dCa bar by dx bar equal to 0. Okay, you see this? So solve this equation with respect to these boundary conditions. Solve this equation with respect to these boundary conditions and get, so once you solve, you will get Ca bar as a function of x bar, and from there we can get Ca as a function of x. Okay, pause and do it for yourself. Pause and do it for yourself. What I want you to think about is, what I want you to think about is what is the physical significance of Thiele modulus? Think, pause and think. Okay, here is the physical significance of Thiele modulus. Phi square is KL square by effective diffusivity. I can write this little differently. I can write this as L square divided by d effective diffusivity divided by 1 by K. Now L square by effective diffusivity is nothing but diffusion time scale. Time required for A to diffuse through the slab. That is the meaning of diffusion time scale. 1 by K is like the reaction time scale. Time required for reaction to get completed, or 63% completed, or that's what we mean when we say reaction time scale. It's like a first order rate constant, right? This you have seen in your undergraduate course. Or if you like, we can think about this phi square as K divided by effective diffusivity by L square. So this would be like a ratio of reaction rate to diffusion rate. Right? So when phi square is far greater than 1, what does it mean? That reaction rate is far greater than diffusion rate. Or phi square is far greater than 1, or phi square is far greater than 1 means reaction time scale is very small as compared to diffusion time scale. Diffusion takes long time, reaction is very fast. That means in this particular case reaction is faster than diffusion. In this case phi square far less than 1, diffusion is faster than reaction. So this condition, reaction is faster than diffusion, means it is diffusion limited. Remember, diffusion and reaction are happening simultaneously. If diffusion is slower, then diffusion is limiting. If reaction is slower, this means it is reaction limited. Limited. Rate determining step is reaction in this case. Rate determining step is diffusion in this case. Another way of defining, here are some definitions that people used in the literature. So sometimes this phi square is also called as Damkohler number. Damkohler number. You will see some in some literatures it is called as Damkohler number. This is called as Damkohler number. We can multiply and divide by effective diffusivity. I'll tell you the reason for doing that. Effective diffusivity. So I can write effective diffusivity into rate constant divided by effective diffusivity by L square. You see, this effective diffusivity by L square is like mass transfer coefficient through the catalyst slab. Remember, it is like mass transfer coefficient in the catalyst slab. So we can write it as KL. So we can write it as square root of effective diffusivity into K divided by KL. Right? This is called as Hatta number. This whatever is inside the bracket is called as Hatta number. Hatta. Hatta number. When we start doing fluid reactions, we will define mass transfer coefficient in this manner, and we'll define effectiveness in this, or we'll define Thiele modulus in this manner. We'll not call it Thiele modulus, we'll call it as Hatta number, and we'll call it by something else as well. Okay. So this is the meaning of physical meaning of the Thiele modulus. Okay. Let's go forward. Here, let me again write diffusion limited. Diffusion is rate determining step. Here it is kinetic limited. Kinetics are rate limited. I want you to draw concentration profile. Let's go forward. So concentration profile, if I want to draw it about this Damkohler number now, right here. Pause, do it for yourself. Phi square far greater than 1, how will the concentration profile look like? Phi square far less than 1, how will the concentration profile look like? Pause and do it for yourself. Then only go forward. Pause. Let me just draw for you. If phi square is far greater than 1 or phi square is far less than 1, phi square is far greater than 1 means diffusion is slow. That means if this is our Ca bar equal to 1 or CAS, it will, by the time it diffuses, it reacts. That means rate of reaction is so fast that it diffuses very quickly. It diffuses slowly but reacts very fast. So concentration of A becomes 0 very quickly. If phi square is far less than 1, diffusion is very fast, reaction is very slow. So if this is our Ca bar or CAS, diffusion is very fast, reaction is slow. So practically everywhere concentration is equal to CAS. Okay, and here it reacts and diffuses inside. Let's go forward. So solve the dimensionless differential equation with respect to these boundary conditions. Do it for yourself. Okay, here's the solution. So if I say d square Ca by dx bar square is phi square Ca bar, boundary conditions at x bar equal to 0, Ca bar is equal to 1, and x bar equal to 1, dCa bar by dx bar is 0. Solve it for yourself. Make sure that you get this expression. Ca bar is cosh, hyperbolic cosh phi 1 minus x bar versus divided by cosh phi. I want you to plot Ca bar versus x bar for different values of phi. Okay. You can take phi less than 1, say 0.1, 0.05, something like that, 0.2, 0.5, 1, 5, 10. And I want you to see how this Ca bar by x bar looks like. Plot this equation, plot it in Excel so that you can easily calculate for, or you can easily see the graph for different values of phi. Plot, and there's an important point that is coming. That's why I'm asking you to plot. Pause and plot. Pause if you have not done it. Pause. This is how your graph will look like. Ca by Cas, which means this is our Ca bar, and x by L, which means this is our x bar. So phi equal to 0.1. This is how it will look like. Phi far less than 1. Remember, phi far less than 1. No diffusion limitation. Diffusion is very fast. Concentration everywhere is inside equal to CAS, which means Ca bar equal to 1, like this case. As phi increases, you will find that the curve shifts, and phi far greater than 1, you will see that Ca bar is practically 0 all the time. Ca quickly gets depleted because diffusion is slow, reaction is fast. Whatever is diffusing is quickly reacted. So Ca becomes 0 very quickly. If you take phi equal to 20, phi equal to 30, take phi equal to 20, phi equal to 30, it will become like this. Lot for yourself. Phi far greater than 1, say phi equal to 20 or something like that, very high, greater than 10. I want to think about what does it mean. What does this tell us about catalyst required for slow and fast reaction? Think, this is the catalyst slab. This is the concentration profile in the catalyst. What does it mean? How do we make, or how do we design a catalyst for very slow reactions, which means phi less than 1? How do we design a catalyst for phi greater than 1, far greater than 1? Imagine that the catalyst is like platinum on carbon or palladium on carbon, very costly. Platinum is very costly, palladium is very costly. Think, pause, write your answer, then only go forward. Then only go forward. If phi is less than 1, phi is far less than 1, what does it mean? Concentration profile is like this, is pink. Concentration profile is like this, CAS, everywhere. Phi far less than 1. That means I require platinum or palladium to be uniformly distributed throughout the catalyst. Right? So we want active sites to be distributed throughout catalyst particle. Otherwise, if they are not distributed throughout the catalyst particle, there will be no reaction here if there is no catalyst. So you want palladium to be present everywhere inside the catalyst, everywhere inside the catalyst. On the other hand, if phi is far greater than 1, what is the concentration profile going to look like? Let me use another color. Concentration profile is going to look like this. CA is going to become 0. Very quickly CA is going to become 0. Concentration is changing from CAS to 0 within a narrow region. So concentration of CA is greater than 0 only in a narrow region near the surface. Near the surface. Concentration of A is 0 beyond a certain small region inside the surface. Concentration of A changing from CAS to 0 only in a small region near the surface. So if my catalyst is costly, platinum, let's say, I want that platinum to be distributed only here. There is no point in having platinum at these locations because there is no A coming there. This platinum is useless. It is not a, there is no A coming on that active site because by the time A reaches there, it is all reacted. So I want catalyst active sites to be present near the surface, not in interior. These are called as egg shell catalyst. How the shell of the egg is a hard material, like that. We want catalyst to be present, or the active part of the catalyst, say platinum or palladium, to be present only on the outer part of the catalyst, outer skin layer, a small layer in the outside. These are called as eggshell catalyst. And then that's how you can reduce the cost. That's how you can reduce the use of platinum or palladium, precious metals, and reduce the cost of catalyst. Okay. So you see, this understanding of this diffusion and reaction is very helpful. We have not done any quantitative thing so far. We have not done any quantitative thing so far yet. Just by knowing the Thiele modulus, just by knowing how the concentration is changing, we can design, we can think about what kind of catalyst we want. That's the advantage of defining things like Thiele modulus, defining, calculating. Okay. Let's go forward. Let's go forward. So now what is the rate expression for the total rate, kilomoles per second, for diffusion into slab? So rate would be, I'm not writing RA, I'm writing total rate, kilomoles per second. Okay. When we say RA, it is per unit volume. So RA is, so rate is minus D effective A dCA by dx at x equal to 0. Again, make it dimensionless. It will become CAS dCA bar, area is there, area of cross section, x bar and L. Okay. So write this, D effective CAS A L dCA bar by dx bar at x equal to 0. I have to, oops, this is my rate expression, cos phi 1 minus x bar cos phi divided by cos phi. I have to differentiate this with respect to x bar and put x bar equal to 0. Cos phi I can take out, d by dx bar of cos phi 1 minus x bar. So that will be sin phi 1 minus x bar into minus phi. So this minus would cancel out. Rate would become effective diffusivity CAS phi by hyperbolic tan phi. You see. Now if there was no diffusion limitation, concentration everywhere would have been equal to CAS. What would have been the rate, total rate in that case? This rate is what we have got here. I want you to divide by rate where no pore diffusion limitation exists, means concentration everywhere is equal to CAS. We can call that as effectiveness factor. How effective the catalyst is. We'll do all these calculations, then it will become clear. So simplify. Eta would become D effective CAS A by L phi tan phi. If there was no pore diffusion limitation, concentration everywhere would have been CAS. Then rate everywhere would have been K into CAS. That will be per unit volume multiplied by volume of the slab A into L. So then this A will cancel out. Cross sectional area. I will get effective diffusivity phi tan phi divided by K L square. And then this K L square by effective diffusivity is nothing but our Thiele modulus phi square. And then this phi will cancel. We will get eta equal to tan phi divided by phi. So when phi is far less than 1, tan phi is nearly equal to phi, so eta is equal to 1. When phi is far greater than 1, tan phi is nearly equal to 1, so eta is 1 by phi. I want you to plot this equation. Plot how eta versus phi. Okay. So now the rate we can easily write. Rate would be effectiveness factor multiplied by KCS from here. See, that's the advantage of defining effectiveness factor. Rate would be eta multiplied by KCS. Of course, now this is per unit volume, per unit catalyst volume. Okay, this is how the plot would look like. Effectiveness factor, effectiveness factor, effectiveness factor on y-axis versus Thiele modulus phi. This is how it will look like. Phi is far less than 1. I wanted to take some values. I will tell you some values and we'll calculate this Thiele modulus and then we'll talk about it a little bit more. Okay, imagine that there is a gas phase reaction. Imagine there is a gas phase reaction. Okay. Effective diffusivity is like 10 raised to minus 6 meter square per second. This should be meter square. Okay, just let me make that correction. Okay, let's take some values and calculate. Let's take some values and calculate. Okay. Imagine there is a gas phase reaction. Effective diffusivity is 10 raised to minus 6 meter square per second. Length of the slab means half the size of the pellet is 1 millimeter, so 0.001 meters. And we'll take different values of rate constant 0.01, 0.1, 1, 10, 100. Let's calculate phi for every case and let's calculate eta for every case. Make sure you get these values. If it's a liquid phase reaction, effective diffusivity is like 10 raised to minus 10 meter square per second. Catalyst particle pellet is like 1 millimeter. Take the same values of rate constants. Okay. Calculate phi, calculate eta. That's one exercise I want to do. Do it for yourself. Make sure you get these values. Next, let's take different catalyst pellets. Size of catalyst pellet. Effective diffusivity is, let's say 10 raised to minus 6 meter square per second. K is 0.1 second inverse. Remember this 0.1 second inverse. Where does that come from? Fast reactions, slow reactions. It is a moderately fast reaction. So L is 0.1 millimeters, 1 millimeter or 10 millimeters. Calculate phi, calculate eta. Do it for yourself. Same way for a liquid phase reaction. 10 raised to minus 10 meter square effective diffusivity. K is 0.1 second inverse. L 0.1 millimeter, 1 millimeter, 10 millimeter. Calculate phi, calculate eta. Do this for yourself. What do we conclude from these values? This slide number 13, as well as this slide number 12. What do we conclude? What do we conclude? Write your conclusions. 1, 2, 3, 4. I'm not saying there are four conclusions. I'm saying you would make your own conclusion. Let's try to conclude from here. You see, if I have 1 millimeter particle like a packed bed reactor, 1 millimeter is half the slab, so 2 millimeter size. Gas phase reaction, even if the gas phase reaction is moderately fast, our effectiveness factor is practically 1. So the conclusion is gas phase reactions in packed beds usually, means for moderately fast reactions, are not diffusion limited. Usually, not always, but because this is the effective diffusivity. If effective diffusivity is less, then this conclusion is not valid. Go to the liquid phase. So liquid phase packed bed, even if the rate constant is small, even if the rate of reaction is slow, these are strongly poor diffusion limited because effective diffusivity is very small, 10 raised to minus 10. So liquid phase reactions in packed beds are usually diffusion limited. Gas phase not diffusion limited means effectiveness is almost 1, means effectiveness is far less than 1, 0.3, 0.1, 0.03. You see, even if the reactions are slow, even if the reactions are slow, what about here? For a moderately fast reaction, if I want to be doing a gas phase reaction, if I'm doing a gas phase reaction, you see, I can easily do this in a packed bed. But look at liquid phase reactions. If I use large particles, effectiveness is far less than 1. I'm not utilizing the catalyst effectively. I need particle sizes of the order of 0.1, means 100 microns. So we can't do this in a packed bed. Pressure drop will be very large. Recall Arjun's equation. Then we need to do these kinds of reactions in a slurry reactor, where small particle sizes are suspended by agitation in liquid. So packed bed reaction is possible for gas phase reactions. Liquid phase, usually we try to do slurry reaction. That's how the hydrogenation, those kinds of reactions are done in a slurry reactor, because those reactions are fast. So if you take a catalyst which is particle, we try to do it in a packed bed, they would be diffusion limited. We are not utilizing the catalyst effectively. We are wasting cost of catalyst. We are wasting platinum. We are wasting palladium. It is not utilized properly. Okay. Then we try to do it in a slurry reactor. Make particle size 100 microns, 50 microns, so that effectively it can be utilized. Reaction can take place very fast. No diffusion limitations. All these, we have not done any calculations, we have not done any um, problem so far. We have not done any problem so far. Just by looking at Thiele modulus, what does it mean? We can make so many conclusions. That's the importance of quantifying everything. That's the importance of expressing things mathematically. Let's go forward. Okay, now I want you to think about this differential equation that we have written for a slab, I want you to write down for other geometries. So our catalyst could be cylindrical in shape. It could be a catalyst pellet, or catalyst could be in the form of spherical particles. Right? So I want you to write down the differential equation for first order reaction, diffusion and reaction in cylindrical or spherical geometries. And then once you write down, how do you define Thiele modulus? That's what I want you to think about. Pause and do it for yourself. Okay, so here is what you would get. Effective diffusivity 1 by R d by dr of R dCA by dr. This is equivalent to d square Ca by dx square in a Cartesian coordinate system is equal to Kca. For a spherical particle, it will be effective diffusivity 1 by R square d by dr of R square dCA by dr. This would be equivalent to d square Ca by dx square for a Cartesian coordinate system equal to Kca. So Thiele modulus we could define as R by 2 square root K divided by effective diffusivity, and for here we would define it as R by 3 divided by square root multiplied by square root K by effective diffusivity. Then if we define Thiele modulus using these definitions, then we can treat it like a Cartesian coordinate system. We can calculate the effectiveness factor from the same expression. Next, I want you to write differential equation for nth order reaction in a slab and then define Thiele modulus for a nth order reaction. We have done it for first order reaction, but I want you to do it for nth order reaction. Pause and do it for yourself. This is how you would get effective diffusivity d square Ca by dx square is equal to K Ca raised to n. If I make it dimensionless, this would become Ca bar and Cas, x bar square and L square. K Ca raised to n, we can make it dimensionless as Cas raised to n into Ca bar raised to n. Okay. Now this one Cas I can cancel, and I'll get d square Ca by dx square is equal to K Cas raised to n minus 1 L square effective diffusivity Ca bar raised to n. So this is now our dimensionless parameter. This we can call as phi square, or Thiele modulus would be L square root K Cas raised to n minus 1 divided by effective diffusivity. Now if you integrate this, if you solve this equation, integrate this, we are not going to do it, but if you integrate this, we will get Ca as a function of x, Ca bar as a function of x, and then same way you can get the effectiveness factor for an nth order reaction. Okay. I'm just going to give you the result. We are not going to derive. I'm just going to give you a result. And in those cases, for large values of Thiele modulus, effectiveness factor is eta would be 2 by n plus 1 raised to half 1 by phi. Phi is defined from here. Okay. So this is how we would use effectiveness factor for nth order reaction. If n is 1, it's like a first order reaction, then this is just 1. Eta becomes 1 by phi, large values of Thiele modulus. So this expression is valid for n equal to 1 as well, for large values of Thiele modulus, not for any other value of Thiele modulus. For nth order reaction, this is how you would define. We are not going to derive this, but you can use this expression for reaction. So if you have an nth order reaction, if you have a, let's say, nth order reaction, and you want to write rate Ra, it would be eta into K Cas raised to n. And what would eta be now? Ra, eta would be 2 by n plus 1 raised to half 1 by phi, and K Cas raised to n. This is how we would write rate of reaction now for nth order reaction, considering pore diffusion and reaction inside the pellet, and then this phi is coming from here. See, rate constant is known, then nth order is known, then I can write rate in terms of this n and rate constant. Okay. All right, so this is how we would use for nth order reaction. Let's go forward. Okay, so estimation of diffusion limitation. So let's say now we have a reaction that is occurring in the plant. Now how do I find for that reaction whether it is diffusion limited or not diffusion limited? Here is one possibility. We can write phi as k L square by effective diffusivity. K L square by effective diffusivity. K can be estimated from observed rate of reaction and concentration. So a pseudo first order rate constant in the plant would be observed rate. What is the rate per unit catalyst volume that is actually happening in the plant? And if I divide by surface concentration or surface concentration, then this would be like a pseudo first order rate constant. R observed I can measure, I can see from the plant material balance in minus out divided by catalyst volume. Rate at which it comes minus rate at which it goes out divided by catalyst volume. That's our R observed. Divided by C, it's a pseudo first order rate constant. I can put that here. R observed L square D effective CAS. Square both sides. R observed L square divided by D effective CAS. So this R observed L square by D effective CAS is called as Weiss-Prater parameter. It has the same meaning as phi square. So when this Weiss-Prater parameter is far less than 1, phi square is far less than 1, reaction is not limited by pore diffusion. When Weiss-Prater criteria is far greater than 1, phi square is far greater than 1. Reaction is limited by pore diffusion. That is the importance of Weiss-Prater parameter. Why? Because this R observed, we don't need to know the rate constant. R observed, this is seen for actual reactor operating. For actual reactor operating, we may not know the kinetics, but we can know what comes in minus what goes out, kilomoles reacted per unit time per unit catalyst volume. This is our R observed. This we can measure, we can actually measure for a reactor operating. Therefore we can calculate, even for an operating reactor we can calculate whether it will be diffusion limited or not. We'll do a problem later on to explain all these things. That's the meaning, that's the importance of Weiss-Prater criteria. Let's go forward. Now one more, external mass transfer consideration. So if there are external mass transfer consideration, what would be the profile look like? This is how the profile would look like. What would be the rate of mass transfer to the catalyst surface? Rate would be mass transfer coefficient, surface area. Now this is surface area per unit external volume, external surface area, not the pore surface area, multiplied by bulk concentration. So KFA is called as volumetric mass transfer coefficient. Remember, A is the surface area per unit volume of external surface. That is where mass transfer is happening, not the pores. We are talking about external mass transfer consideration. Understand all these things. So now we can compare this KFA and CAB with our observed rate. So if our R observed is far less than R mass transfer, then what does it tell you? Mass transfer is not limiting. So if R observed is far less than KFA CAB, then there is no mass transfer limitation. I can bring this on the other side. R observed divided by KFA CAB. If this value is far less than 1, then we know that it is not external mass transfer limited. And surface area I can write in terms of 6 divided by particle size if sphere diameter if it is a spherical particle. So this is called as Mears criteria. Just by looking at R observed, by measuring actual observed rate of reaction in the plant, knowing the particle size, estimating the mass transfer coefficient, bulk concentration we can measure, we can check whether external mass transfer is limited or not limited. That's the importance of Mears criteria. Okay. Understand all these, don't go forward. When we do problem, all these things will be even more clear, but before we do problem, make sure that you have understood all the concepts that are talked about in this lecture. Now let's say all the three things are important: external mass transfer, pore diffusion, and kinetic limitations. I want you to draw concentration profile. Pause and draw. This is how it will look like. There will be mass transfer resistance, there will be diffusion inside, and then the diffusion inside will be limiting. Reaction is there, but reaction is not so fast enough as to make this CAS equal to 0, Ca inside equal to 0. There is still some finite Ca in the bulk of the catalyst. This Ca is non-zero. So this is how we can now write it. I want you to write rate of expression Ra. Derive for yourself. Pause and do. Here is a possible answer. Don't go forward till you have derived yourself. Here is the possible answer. Right? I want you to write overall rate of reaction. If you have not paused, pause now and derive. Rate of mass transfer. What is rate of mass transfer? Rate of diffusion and reaction inside catalyst pellet. Write these expressions and simplify. I'm giving you a chance. If you have not paused, pause now and do it for yourself. Rate of mass transfer would be KFA CAB minus CAS. Bulk concentration minus the surface concentration. This mass transfer step. Diffusion and reaction inside the catalyst pellet. We know that Ra is eta, K and CAS. So we don't have to know concentration inside. That is the importance of defining effectiveness factor. I don't have to know what is there inside. I don't need to measure. I can just define everything based on surface concentration at the surface. Surface concentration also is not easy to measure. I can't take a sample and measure. Bulk concentration I can measure in the bulk of fluid. So eliminate CAS from these two equations and simplify. Pause and do it for yourself. So Ra would be Ca bulk divided by 1 by KFA plus 1 by eta K. This is like two resistances in series. One is a mass transfer resistance and second is diffusion and reaction resistance. In chemical engineering we come across many such occasions where we have resistances in series. Okay, we'll use this expression for now our problems. Okay. So we'll stop this lecture here. I want you to read and revise from the textbook, Fogler's book, 4th edition. We are on chapter 11 and 12. Read the theory and make sure you have understood all this before we go forward to problems. We'll stop this lecture here. Make sure you have understood physical meaning of all of these things: effectiveness factor, Thiele modulus, Weiss-Prater parameter, Mears criteria, pore surface area, external surface area. Make sure you have understood all these concepts before you go to the next lecture. Okay, we'll stop this lecture here.